So this is the last talk of the fall session for this year, 2020. So I'm glad to present today Olivier Wittenberg for Paris Nord University. He's going to speak about Massey products in the Galois cohomology of number fields. So please go ahead.
Thank you very much. So first, thanks to the organizers for the invitation to speak in this seminar. It's a pleasure. And thank you everyone for joining the room. So I will talk about a joint work with Yonatan Harpaz about Massey products in the Galois cohomology of number fields. So I'm addressing non-experts. So the goal will be to explain a result and the strategy of the proof of a theorem that's about a conjecture of Mináč and Tân. So the plan will really be, I will spend some time talking about Massey products, trying to motivate the theorem and explaining the conjecture. Then I will, but this is about Galois cohomology. And then I will explain how geometry and homogeneous spaces of linear groups come into play. Geometry. And finally, to prove the theorem, which is about number fields, we'll have to think about local global principles. Okay, so that's the rough plan for the talk. So please don't hesitate to interrupt me at any point for any question. So, okay, let's start with Massey products. So everyone knows the inverse Galois problem. You start with a finite group and you ask whether it can be realized as the Galois group of a field extension of a given field. For number fields, conjecturally, the answer is any finite group. Okay, it's very far from being known, but this simple conjecture. Here's a question which looks like this one, but which is a bit different. You start with a profinite group, gamma, and you ask, can it be realized as the absolute Galois group of a field? When is gamma isomorphic to Galois of k bar over k for some field k? So here, the base field is not prescribed, and we're only looking at the absolute Galois group. So that you could call it the absolute inverse Galois problem. So contrary to the inverse Galois problem, this is even conjecturally extremely open. We don't have a conjectural answer to this, but we do have a few necessary conditions which are known. So a rather elementary one is the fact that there is no, if gamma is an absolute Galois group, then there's no element of finite order except order 2. No element of finite order different from 1 or 2. So this is Artin-Schreier theory. Essentially, elements, Schreier theory, essentially elements of order 2 correspond to real closed fields sitting inside of k bar with index 2. And that's the only thing that can happen. You cannot have finite sub-extensions of k bar such that k bar is finite over it, except this. Okay, beyond this, there are deeper necessary conditions. So for example, you can look at the cohomology of gamma with values in Z mod 2Z. You take all degrees. This is a graded algebra. And as a graded algebra, if gamma is an absolute Galois group, this must be a quadratic algebra. By which I mean it's generated in degree 1, and the relations are in degree 2. And this is a consequence of the Miller conjecture proved by Voevodsky, which, according to which this is just the algebra of K theory, Miller K theory mod 2. So, and then by definition of K theory, of Miller K theory, this is quadratic. Okay, Miller's conjecture. So this is an example of a necessary condition, which is quite deep. And as we know, Milner's conjecture is a particular case of the Bloch-Kato conjecture. And well, you can spell out other necessary conditions, which are consequences, other consequences of Bloch-Kato. So I'm not claiming to write a complete list here. And there are yet other necessary conditions which are known, though nothing like this is expected to be a complete answer. One necessary condition that you could think of has to do with Massey products, and that's the next topic, and that's what will motivate. I mean, this question will be the motivation for us. But let me now switch to Massey products. Okay, so but first I need to introduce them in general. So that's something which exists in almost any cohomology theory. So let's first discuss some generalities. So let's take some coefficient ring R, a commutative ring. And let's work with cohomology of something. It could be a topological space. Let me call it X, a topological space, or it could be a profinite group. A profinite group, or it could be really anything. Any site with fiber products would do. Okay, so given X and R like this, we know how to construct cohomology of X with values in R. And well, this is a graded algebra over R with cup products. And as we know, this is obtained from a cochain complex by passing to cohomology. Cochain complex, which I denote C star, XR. Cochain complex. Oops, complex. So it's a complex, so there's a differential, let me call it D. So if X is a topological space, you can think of the complex of singular cochains, for example, or if X is a profinite group, you can think of the cochain of this, the standard cochains, standard resolution, the standard way to compute cohomology of a group. Or there are many other choices in many other contexts. But in all of these situations, this is not just a complex of a billion groups. There's a multiplicative structure. So namely, on the direct sum of the CIXR, you have a multiplication. So that's a graded algebra in a way that respects the differential like this. D of xy is dxy plus minus 1 to the power degree of x dy. So that's what's called a differential graded algebra. And this multiplicative structure here is what induces the cup product when you go to cohomology. Okay, so all of this is very standard. But now what's important here is that when you pass to cohomology and you consider the multiplicative structure, you actually lose some information. So you get the cup product, but you lose some homotopical information, which vanishes when you just look at homological information like this. And some of the information that you lose here when passing to cohomology, you can recover it in the form of additional structure on the cohomology, in particular as Massey products. So that's where they come from. So plus Massey products. Okay, so and I will tell you more exactly what these are, but they are not very nice products. First, they are not always defined, and when they are defined, they do not take just one value in general. They are multi-valued, so that's something which is quite badly behaved, but it's an invariant which exists, so we have to consider it. Okay, so a piece of notation because of this bad behavior. So so the Massey product of, so we'll consider classes in H1 only. mean, you can consider Massey products of other classes, but in this talk, it will only be H1. So the Massey product of any number of classes, A1, AN in H1 XR. So sometimes it's not defined, as I said, and sometimes there are several values. So we always see it as a set of values. So it's a subset of, okay, so if you start with classes in H1, no matter how many classes you take, you will take values in H2. Subset of H2 XR. Okay, and we denote it with angle brackets. So just as a matter of convention, we say that the Massey product is defined when this subset is non-empty. So there's at least one value. And we will say that it vanishes when when 0 is one of the values it takes. Okay, this is standard terminology in the field. Okay, so example, well, if n is equal to 2, then the Massey product is just the cup product. And so that means it's the singleton cup product. If n is equal to 3, so as I've told you, it's not always defined. So actually it's defined exactly. So A1, A2, A3 is defined exactly when the cup products A1, A2 and A2, A3 vanish. So you should think of Massey products as secondary operations. You have 3 classes. Well, you take the consecutive cup products. Maybe they don't vanish. Okay, then you have a product. If the 2 consecutive cup products vanish, then you can look at the Massey product, and so on and so forth. So the same for n greater than 3. The Massey product will be defined only when some smaller Massey products vanish. So in this sense, they are secondary operations. So let me give you the full definition of the Massey product with 3 classes so that you can see what it looks like. So you start with A1, A2, A3, which are cohomology classes. First, we lift them to co-cycles. So let A1 underlined, A2 underlined, A3 underlined be co-cycles Z1X with values in R that represent A1, A2, A3. Then consider the product A1, A2. So this is the product of cochains. So this is a cochain a priori. And okay, I've told you it's defined only when the cup products vanish. So that means this cochain will be a coboundary. The cohomology class of this product will be 0. So you write this as the differential of some cochain that you write A12 underlined, and the same with A2, A3. So the product will be the differential of some A23 underlined. Okay, so for A12, A23, some cochains, C1, XR. Okay, then what you can do is consider this formula. You look at minus A1 times A23 plus A12 times A3. Okay, well, this is some cochain of degree 2. And what I claim is this is actually a cocycle. You can check it. So then this is in Z2 XR. So it has some cohomology class. And the Massey product is exactly the set of all cohomology classes that you can obtain in this way. A1, A2, A3. That's the set of all classes in H2 XR obtained in this way. So you see, I mean, there are choices here. I've chosen A12 and A23. So that's why you get several classes in general. And now it's clear that this thing is defined exactly when the cup products here vanish. Okay, so that's the definition. And already for n equals 3, this is, despite the definition, which looks a bit bad, it's already a very useful invariant. So let me recall the first application of this. So in topology, you can look at loops in 3 space. So let's L in R3. Let this be a disjoint union of 3 loops. So for example, you could think of the trivial disjoint union, put them in a plane and a plane in 3 space. Or you could consider a very subtle configuration called the Borromean rings, which I've prepared here. So I put it here. So this, let me call it L1. So, okay, it's a standard practice in topology when you have a configuration of circles, of loops in 3 space, you try to find topological invariants to distinguish them up to, say, isotopy. So here, what I'm telling you is that the Massey product is going to be able to distinguish between L0 and L1. So here, L1 Borromean rings, it's a situation where each pair of circles is not linked. But despite of this, the 3 circles together, well, you cannot unlink them all. So, and the way you can see this with Massey products is as follows. You compute the cohomology of the complements R3 minus L with coefficients in Z. And well, you can compute this and you can check that if you take L0 and L1, you get the same cohomology groups. And if you look at the cup products, the multiplicative structure coming from cup products, you still get isomorphic graded algebras as graded algebras. And the reason is that the cup product here is only capturing the linking numbers of 2 circles, of any pair of circles. But here, any pair of circles is unlinked. Okay, but you can compute that these 2 things are not isomorphic as graded algebras endowed with Massey products. So as graded algebras plus Massey products. In fact, if you choose orientations of the circles, each circle will give you a class in H1, and the Massey product of these 3 classes here is going to be actually non-vanishing. It's going to be a singleton at non-zero, and here it's going to be 0. So it's a computation. And that was Massey's original example. Okay, and that's very nice because it tells you already that these complements, R3 minus L0 and R3 minus L1, are not isomorphic as topological spaces. They're not even homotopically equivalent. Okay. So that's a motivation for n equals 3. There's a definition which goes on for n greater than 3. I'm not going to give it now. Things get even worse. For n at least 4, for example, if you want to characterize when the Massey product is defined, it's not enough to ask for the smaller Massey product to vanish. This is a necessary condition, but not a sufficient one. So things get more and more complicated, but still, I mean, these things exist. And I'd like to mention another standard theorem which motivates Massey products. So they can be used to restrict the homotopy types of some manifolds. Namely, there's a theorem of Deligne, Griffith, Morgan, and Sullivan that says that if you take a compact Keller manifold and rational coefficients, then the Massey products are as trivial as they can be. That is, if you take at least 3 classes in H1, the Massey product vanishes as soon as it is defined. So maybe it's not defined, but if it is defined, then it vanishes. And this gives a restriction on the possible homotopy types of compact Keller manifolds. And that's for any n. Okay, so now let me come to Galois cohomology. So here's the conjecture that we're interested in today. Conjecture by Jan Mináč and Nguyen Tân. So 2013. So the conjecture is that if you take the absolute Galois group of a field, any field, Massey products with coefficients z mod pz for p prime number should vanish as soon as they are defined. So they should be as trivial as they can be. So take k a field, p a prime, n an integer at least 3, and a1 a n in h1 k z mod pz. Then the Massey product a1 a n vanishes if it is defined. So again, let me repeat. This means this set is contains 0 if it is non-empty. So the point of this conjecture is that it would give new restrictions on the absolute Galois groups of fields. So going in the direction of the question I started with. So and I mean new restrictions that are not covered by the Bloch-Kato conjecture, which is a theorem. So okay, there's been a lot of work on this. So let me very briefly say a few things about the history. So actually, this started with the work of Hopkins and Pickelgren before the conjecture. So who proved that this is true for number fields when you take 3 classes, n equals 3, and coefficients z mod 2z, p equals 2. Then there was a lot of work by Mináč, Tân, Efrat, Massey, Mináč, Tân, Efrat, Massey, which led to 2 main results. So this was 2013, 2014. So first, true when n equals 3. So this is due to Mináč and Tân. N equals 3 for any p and any field, k. And if you look at local fields, it's true in complete generality. So true when k is a local field. So by local field, I mean completion of a number field at a place, of a global field at some place. Okay, so this second statement is actually easy. It's a consequence of state duality. So the thing is, you're looking at classes in H2 k z mod pz, but when k is a local field, this group is very small. It's 0 or z mod pz, so there's not much room in there. So okay, this is something easy. So here the theorem is really for n equals 3, any k, but still it's important to know that it's true over local fields. Okay, and then there was a work by Galois, Mináč, Harpaz, and myself, 2016, which took care of the case K number field n equals 4 and p equals 2. So okay, these works follow a common strategy, which is trying to work with splitting varieties. So that is trying to construct varieties such that the existence of a rational point on the variety is equivalent to the vanishing of the Massey product we're considering, and then producing rational points on these splitting varieties. So in each case, they exhibited a splitting variety and I had to understand it. So here already in this work, the splitting variety for n equals 4, p equals 2 was rather complicated. And we were stuck here for n equals 4 and p larger than 2. So my co-authors could construct splitting varieties, at least under some genericity assumption, but we were stuck when trying to understand the arithmetic. So using a slightly different strategy, but still based on splitting varieties, what we did with Yonatan Harpaz, and that's the main theorem for today, is prove the conjecture for number fields in general. So Harpaz and myself. So the conjecture is true for K number field, any n, any p. So that's what I'm going to explain in the rest of this.
Okay, we do not see you at the bottom. Yes.
Sorry, better like this? Yeah. Okay.
Yes, that's fine. Thank you.
Thank you. Okay, so that's what I'm going to explain in the rest of the talk. So as I've tried to explain, the motivation for this is that it gives new restrictions. I mean, new information on the absolute Galois group of Q. It gives new restrictions on the possible absolute Galois groups of number fields. It tells you, okay, well, these Massey products have to vanish for gamma to be the absolute Galois group of a number field.
How do you know it doesn't follow from block-Cotter?
No, okay, I don't have a proof of this. Sorry. Okay, I guess we should ask Jan. No, I don't have a better answer. Sorry. I would say that experts have tried to work hard exploiting block Kato and could not, I mean, could not exclude certain groups that are excluded by this. But I mean, it's not a mathematical proof. Okay. Okay, so okay, so the strategy. I mean, we know that the conjecture is true for local fields. So okay, to go from local fields to number fields, it's enough to have some local global principle. And since we're working with classes in H2, the situation looks good. If you start with, and this is the situation for n equals 2. N equals 2, you're just looking at a cup product. A cup product is one class in H2, and it's well known that a class in H2, say with Z mod 2Z coefficients to simplify, is trivial if K is number field. If it is locally trivial, that's the local global principle for conics. But the problem for n greater than 2 is that this Massey product is multi-valued. So to say that it vanishes is just saying that locally it contains 0, but that doesn't tell you that one single class is vanishing everywhere locally. So there's a problem, and that's why everyone goes through splitting varieties. So that's what I'm going to explain now. So splitting varieties. Sorry, I called this geometry earlier. So okay, let me work with any field of characteristic 0. And okay, but let's work with coefficients Z mod PZ from now on. And okay, n at least 2. And let's fix cohomology classes A1, AN in H1 of K with values in Z mod PZ. So, okay, gamma K will be the absolute Galois group. So, okay, let me write this down. A splitting variety for the Massey product for the Massey product of A1, AN. So by definition, it's just a variety V over K, such that whenever you have a field extension, say L over K, well, V has an L point if and only if the Massey product vanishes over L. So that is A1, AN, when you do the computation over L, so as a subset of H2 L Z mod PZ, contains 0. Okay, that's the definition. And so again, for n equals 2, this is just the cup product. So that's the first example. If you take n equals 2 and p equals 2, it's well known that splitting variety for the cup product of two classes in H1 Z mod 2Z is given by a conic. You take the conic A1 x squared plus A2 x squared y squared equals 1 equals, well, Z squared. Projective conic. Okay, so people have tried constructing explicit splitting varieties for n equals 3 and 4. So this has been done, but we need something else. And so we're going to rely on a construction due to Pal and Schlank of splitting varieties for Massey product in general. These splitting varieties in general are homogeneous spaces, so they are not very explicit, but well, at least they exist. So let me explain how this works. So some notation first. Let's alpha denotes the morphism from gamma k to Z mod PZ to the power n given by A1, AN. So each AI is a morphism from gamma k to Z mod PZ. Okay, so this is A1, AN. And we're going to work with the group of, we're going to work with matrices with coefficients in Z mod PZ. So let U be the group of upper triangular unipotent matrices. So I put 1 on the diagonal, 0 here. Yeah, here, anything here. So inside of GL n plus 1 Z mod PZ. Okay, so this is a finite group, and we're going to be interested in its center, Z, which is just the group of matrices with possibly one non-zero coefficient here in the corner, and everything else 0. Oops. Okay, so this is the center. And the reason why we're interested in doing this is that we can now, so let me go to another page. We can now, like this, we can now consider this sequence 1 Z U mod Z. And so U mod Z, so there's a natural map here from U to the abelianization of U, and this factors through U mod Z. So what is the abelianization? It's just Z mod P to the power n, if you think about it. And this is given by the coefficients just above the diagonal. So starting from a matrix here, you just remember the coefficients here immediately above the diagonal. And this gives you the image in the abelianization. Just, okay, and we're working with matrices of size n plus 1, so there are n of them. Okay, so the reason why I'm doing this is that now we have a very nice interpretation of Massey products, which you can take as a definition, if you like, for n at least 4. and it's the following. So we start with our gamma k, with our alpha, sorry, which gives a map from gamma k to z mod pz to the power n. So these are the classes of which we're taking the Massey product. And what we do is that we look at liftings of this alpha to maps to u mod z. Let's consider liftings like this, alpha tilde. Okay, and then there is this very nice theorem of Dwyer, 1975, which tells you like this, which tells you the Massey product of A1 AN is exactly the set of classes in H2 which you obtain as follows. Start with alpha, lift it in some way to some alpha tilde, and then take the boundary map. So alpha tilde, you can view it as a class in H1 K U mod Z. And there's a boundary map, delta, from H1 K U mod Z to H2 K Z. This is non-abelian cohomology, but it's a central extension. So this boundary map does exist. So you take the boundary of any lifting, that gives you a class in H2K Z, and Z here is just Z mod PZ. Okay, so this is H2K Z mod PZ. And the set of classes that you can obtain in this way is exactly the Massey product. So it's exactly the set of delta of alpha tilde when alpha tilde varies over all of the lifts of alpha. Okay, so you can check, I mean, it's an exercise to check that for n equals 2, this does give the cup product. So here you're looking at 3 by 3 matrices. It's a small computation. So I leave it as an exercise. For n equals 3, it's a slightly more involved exercise to check that it's the same definition. I mean, it coincides with the definition I gave before. And for n at least 4, you can take it as a definition if you like. So the point of this is that we've got rid of the differential graded algebras and of the cochains, and now we're looking just at non-abelian group cohomology. Okay, and from then, we construct the splitting varieties, so following Ambrosch-Pahl and Thomer-Schlank, like this. So we fix an embedding of U. So here it can be a bit confusing. U is a group of matrices. It's a finite group. The matrices have coefficients in Z mod PZ, but we embed it into SLN of K for some N. Okay, it's just some finite group. We can embed it into SLN of K. And then what we do is we consider alpha. So alpha is giving us a class in H1 of K UAB. So it classifies some torsor under UAB. So let E to spec K be the torsor under UAB classified by alpha. And now we have this geometric construction, which is that we consider SLN mod U prime, the derived subgroup of U. This goes to SLN mod U, of course. So, sorry, what is this SLN mod U prime and SLN mod U? Here I'm looking at SLN as an algebraic group over K, and U prime as a constant subgroup. Okay, it's a subgroup scheme. I take the quotients. So now this projection here is also a torsor under UAB. Okay, so we have this sequence, 1 U prime UAB. And what I do is that I twist this torsor with this one. And this gives me the splitting variety I'm interested in. So definition is V. So one compact way of seeing it is we take SLN, we take the product with E, and we mod out by the diagonal action of U. So U acts on SLN by multiplication through the embedding, and it acts on E through UAB. Take the diagonal action, the quotient. So this is really just what I've told you, the twist of this torsor by this one. Okay, and so the theorem is that this is indeed a splitting variety. So due to Paul and Schlank, V is a splitting variety. For the vanishing of this Massey product. So let me just say one word about why this is so. So I mean, it's not a proof, but at least one direction. Well, you can consider the fundamental exact sequence, the sequence of pi1s, étal pi1s for V. So V over k bar. So I choose some base point, some geometric base point, goes to pi1 et of V, goes to gamma k 1. Well, here vk bar, so you have to remember that geometrically, so E is trivial as a torsor, so it's like U ab. So geometrically here, this is just SLN mod U prime. Vk bar is geometrically SLN mod U prime. So the fundamental group, sorry, I wrote too low. So the fundamental group, because SLN is simply connected, the fundamental group of this quotient is U prime itself. This is U prime. And as you can guess, the sequence you obtain here is related to this sequence U prime, U ab. Namely, here we have this map alpha that we started with. And you can check that there's a map here which makes the whole diagram commute. So that the sequence on the top is induced from the sequence on the bottom by just pulling back through alpha. Okay, and the reason why this is interesting is that at least you see that if V has a rational point will give you a section of this, of the first exact sequence up to conjugation. And a section here induces a lifting from gamma k to U of alpha. So let me call this alpha 0. Okay, but so if V has a rational point, there is such a lifting. But what does it mean that there is such a lifting? Let's go back to Dwyer. Well, to say that there is a lifting all the way here to U is saying that there is a lifting alpha tilde whose boundary is trivial. And that is exactly saying that the Massey product contains 0. Okay, so here what I've showed to you is that if V has a rational point, then indeed the Massey product vanishes. So you have to prove the converse, and that's what they prove. Basically, you have to prove that any section of this sequence here comes from a rational point. Okay, but that's how it is. So now we have this splitting variety, and we have to work to find a rational point on it when K is a number field. So that's the third part. So from local to global. So now K is a number field. And so the question is this. So assume, so we have to use this hypothesis, assume that the Massey product is defined. Okay, then prove that V has a rational point. Okay, so we know, because the conjecture is true over local fields, we know that V has local points in every completion of K. So that means that V has an adelic point, if you like. So, okay, it would be enough to have a local global principle. If V has an adelic point, does it imply that V has a rational point? Well, in general, such things completely fail. There are some obstructions which are understood, namely the Brahmanin obstructions, among others. And so the Brahmanin obstructions, which are based on global reciprocity law from class field theory, tells you that in many examples, you have varieties which have local points, but no global points. So, okay, let me recall what this is. So here, let's introduce a smooth compactification of V, X, smooth compactification. So it's a smooth proper variety over a number field. And so what Manin did, so this is something which has a meaning for any smooth proper variety. So you can introduce between the adelic points of X and the rational points of X, you can introduce an intermediate set, which is the Brahmanin set. So you have rational points inside of adelic points, so embedded diagonally. So inside you have the Brahmanin set. So it's denoted like this. It's defined in terms of the Brouwer group. So Brouwer group of X, that's H2 et al. Of X GM. And okay, I mean this definition, which is it's the set of adelic points, collections of local points, which have the property that for every class beta in the Brouwer group, if you evaluate beta at PV, then you get a class in the Brouwer group of KV. You can take the local invariant from class field theory. So that's an element in Q mod Z. And you take the sum over all places. This sum has only finitely many non-zero terms. You require that the sum be 0 in Q mod Z. Okay, this is just a definition, but it turns out that this intermediate set contains rational points, because if all of the PVs come from a single rational point, then all of the beta of PVs come from a single class in the Brouwer group of K, and it's well known that the sum of all of the invariants is 0. That's the global reciprocity law. So, okay, that's something that can explain why there's no rational point. It could be that the intermediate set is empty even though there are local points everywhere. So, okay, how to overcome this problem? Well, fortunately, for some homogeneous spaces of SLN, as the V that we're considering, we have theorems that go in, that refine this implication here and that tell you if there's no Brahmanin obstruction, then in fact there is a rational point. So one such theorem is the following. So theorem. So something that we proved with Yonatan Harpaz a few years ago. So take X, a smooth compactification of a homogeneous space of SLN, and you assume that the stabilizer of a geometric point is finite, but more than that, it's a super solvable group. So, with finite super solvable geometric stabilizer. So here, okay, super solvable means it's something which is stronger than solvable. It's weaker than nilpotent. It means that you can find a filtration of your finite group by normal subgroups. Each subgroup is normal in the big group, and the quotients are cyclic. So the difference with solvable is that you require normality in the big group and the quotients to be cyclic. Okay, so the theorem is that if you have this assumption, then as soon as the Brahmanin set is non-empty, you have rational points, and in fact, lots of them. Rational points are Zariski dense. In X. Okay, so here, one word of warning here, supersolvable is not just as a finite group. It's a finite, you should think of the stabilizer as a group endowed with an outer Galois action. And this definition of supersolvability we use here takes this outer Galois action into account. So let me not be too precise, but taking into account the outer Galois action on the stabilizer. Okay. Okay, so this is something that we proved a few years ago. And the conclusion is that, well, we'd like to apply it to our splitting varieties. So something that I perhaps did not emphasize enough is that this V here is a homogeneous space of SLN. I mean, the action of SLN by multiplication on the left here descends to this quotient. And the stabilizer of a geometry point is this U prime with an outer Galois action that comes from alpha here. Alpha gamma acts through U ab, which then has an outer action on U prime. And we're very fortunate that this U prime is indeed supersolvable, including when you take into account the outer Galois action. V has a supersolvable geometric stabilizer. So this isn't something that should be checked. It's easy to check, so I just ignore it for now, but it's true. And we're very lucky because thanks to this, we can apply the theorem to V. And the conclusion is that in order to prove the existence of rational points on V, which is an open subset in X, it's enough to prove that the Brahmanin set for X is non-empty. It's the only thing we have to prove now. So, okay, now we need this. X of AK, Bra of X is non-empty. It's the only thing we need. Whoops, okay. Okay, so how does one do such a thing? So first, one has to approach the Bra group itself. And that's, in general, difficult, how to approach the Bra group itself. So already, over an algebraically closed field, it's something which is not easy to understand. So fortunately, for homogeneous spaces of SLN, there's a formula over algebraically closed fields due to Bogomolov, 1987, which is as follows. If you take xk bar, smooth compactification of SLN k bar mod G, G finite, then the Bra group of xk bar is computed by the following formula. It's the kernel of H2 G Q mod Z going to, by restriction, H2 of any bicyclic subgroup. H2 of A Q mod Z. A in G, a bicyclic subgroup. Bicyclic means generated by two elements. Okay. So, okay, that's a formula. And here our group is U prime. So you ask, okay, what does this give for U prime? And the answer is not so easy to obtain, but it's known. We're very lucky. There's a theorem of Mikhailov, which does exactly this. Mikhailov, 2013, for G equals U prime, you get 0. Sorry, okay, get 0. So, okay, we're happy. There's no problem with the Bra group coming from the algebraic closure. Still, there is the so-called algebraic Bra group. So the classes which die when you extend the scalars to the algebraic closure. So Bra 1 of X, that's so the kernel of Bra X going to Bra of X K bar. And you have to understand this. So here, the way to analyze this is by using the Hochschild spectral sequence, but actually not for X, because X is some smooth compactification, we don't know it, but for V. So what we do is we consider the Bra group of the algebraic Bra group of X modulo the classes coming from the base field, which play no role. And by restriction, this embeds into the same thing for V, the dense open subset, which is the homogeneous space. Ra1 of V modulo the image of the constant classes. And now the Hochschild spectral sequence tells you that exactly this quotient is computed as Galois cohomology H1 of K with values in pic of V over K bar. Okay, and pic of V over K bar in this case is easy to compute. This pic is the Cartier dual of the abelianization of the stabilizer, which in this case is U prime. U prime ab Cartier dual. Okay, so we have this nice formula here for a group which contains the group we're interested in. Now, you have to be careful. Here on the right, this group here is in general a huge group, infinite. So typically this Cartier dual could be just Z mod 2Z. But on the left, this is a finite group. There are only finitely many classes which play a role. So the problem now is how to exactly determine this finite subgroup of this big infinite group. So there's a tool for this. It's actually a formula which tells you which classes here extend to the whole of X. So this is a finite group identified by a formula which I will not write, but which is due to Demarche, 2010. And it, in terms of non-abelian cohomology, it's a bit subtle. Okay, and so now I can finally state what we really do in this work after all of these reductions and strokes of luck. Well, it's exactly what remains to be done. So, sorry. So theorem. So really what we do is we prove that if the Massey product is defined, then, well, there's an adelic point of X which is orthogonal to the algebraic part of the Bra group. So there are two things that go in. This is the core of the theorem, and it is this statement which is hard to prove and which takes a lot of work. So I'm not going to explain, of course, the proof completely. That's impossible. But let me just say that there are really two aspects. So one is using the formula by Demarche computes the Bra group. And this is really this amounts to some very delicate properties in terms of non-abelian cohomology, and you very quickly have to look at this group U, the group U prime, and the group theory of these groups. It becomes really involved, but somehow we managed to understand enough of this group for this step. So on the one hand, you have to understand the Bra group, And on the other hand, you have to construct local points. And here it's important to emphasize that, yes, there are non-trivial classes in the Brouwer group. So it's not enough to just know that V has local points. The existence of a collection of local points will not be enough to deduce the existence of a rational point. You want to construct local points which are orthogonal to the classes in this algebraic Brouwer group, which we managed to understand using the Marsh. So it's not any local points, but it's really local points which are sufficiently well behaved let's say with respect to a lift. So let me come back to a few pages earlier. So this diagram here. So recall, we start with alpha. These are the classes that we're taking the Massey product of. And we assume that the Massey product is defined, which means that there is at least one lifting here, alpha tilde to U mod Z. And we want to prove that the Massey product vanishes, which means that there is a lifting of alpha to alpha 0 here to U. Okay, so at least we know that there is some alpha tilde, and the local points that we have to construct here have to be sufficiently well behaved with respect to a choice of alpha tilde, gamma k to U mod Z, lifting alpha. So yeah, in fact, so my time is up, so let me just write one more line. So in fact, there's a dichotomy in the argument which appears. Things turn out to be much easier when n is at least 7. In fact, when n is at least 7, we construct an element in the Brahmanin set of V AK, Brouwer 1 V, which is inside X of AK, Brouwer 1 X. So as I've told you, Brouwer 1 of X is a finite group modulo the constant classes. Brouwer 1 of V, on the contrary, is this huge group here. So it's quite surprising that we managed to satisfy all of these infinitely many conditions at once. But in fact, things are easier really for n at least 7. And we can, even without thinking, construct an element here, and then we're done. But for n equals 4, 5, 6, we really have to work more to analyze the Brouwer group, the exact Brouwer group, and the construction of local points sufficiently well behaved with respect to some alpha tilde. Okay. So let me just write this, work more. Okay, my time is up. Thank you very much for your attention.
Thank you, Olivier. Comments, questions? So you can use the chat if you don't have any microphone.
So why P equals 2? Don't you want to consider the Brouwer varieties? The splitting ones?
I'm sorry, I'm not sure I understand the question. If P is equal to, why should several Brouwer varieties help? So when n is equal to
if P is greater than 2, so what happens if P is greater than 2, or don't you assume that P is 2?
I'm sorry, so in the proof of the theorem, I'm not making any difference between P equals 2 and P greater than 2. So the splitting varieties
I'm sorry.
Yeah, the splitting varieties that we use are these homogeneous spaces of SLN. So before, so sorry, I lost the page. Yeah, here I give this example here that if n is equal to 2 and p is equal to 2, so n equal to 2 means you're looking at just 2 classes in H1. So then there's a splitting variety for the. So I mean, if you're just looking at 2 classes, the Massey product is the cup product. You're just looking at 1 class in H2, and this class is well known, is trivial if and only if this conic has a rational point. So here, if n is equal to 2, but p is greater than 2, then, well, let's say the pth roots of unity are contained in the field, then yes, you can use a Severi-Bra variety instead. It's the same, I agree. But if n is greater than 2, then I mean, no, I mean, even if p is equal to 2, I mean, things are more complicated. You cannot just write a conic. I mean,
Okay,
does this answer your question?
Some part of your, yes. Sorry.
Okay, another question?
In the case where n equals 3, is your approach different from the previous proof?
Okay, so there are several proofs. So the first proof was for number fields. I didn't number my pages. Now I'm lost. So here. Yes, no. Sorry. So yeah, it's here. So the first proof for number fields was, the first proof for n equals 3 was for number fields by Hopkins and Wittenberg. So their approach was to exhibit the splitting variety, and it turns out, so they managed to write one for n equals 3, p equals 2, which was not a homogeneous space of SLN with finite stabilizers, but it was actually a torsor under a torus, a very explicit one. And it turns out that torsors under this type of torus exactly satisfy the Hasse principle. This was a theorem of Leap and Wadsworth. And I mean, you can compute the Bra group in that case and check that it's trivial. So that was the approach of Hopkins and Wittenberg. Then there were other proofs later given by these authors. So in particular, now, I mean, how things are understood for n equals 3 is a bit different. So now really the proof is you write down a splitting variety and you write down almost an explicit rational point on it over any field. And of course, if the conjecture is true, then one should be able to do the same for any n. But of course, we don't know how to do it.
Okay. One other questions, maybe? Yeah.
May I ask, is it like perhaps you can, Olivier, thank you very much. It was a great talk. Yeah,
Thank you.
Can you perhaps comment a little bit about some explicit possibility of explicit construction from your thing of unipotent extension of algebraic number fields?
I'm sorry. I mean, you're the expert on this, so.
Yeah, I was just wondering whether your particular construction will give some explicit version or possibility of explicit version.
Yeah, I understand. I would say no, but I haven't thought very much. So yeah, what Jan is alluding to is that for n equals 3 or n equals 4, when you write the splitting varieties that appear in these works I quoted, I mean, the explicit form of these varieties allows you to solve these embedding problems in a rather explicit way. So I mean, so here you see, by looking for a lift alpha 0, we're really looking for an extension of K Galois with group U and things like that. So starting from the splitting variety, the explicit one that they have, they can produce in a really explicit way that you can really put in a computer and find numerical examples. You can solve these embedding problems. But starting from the splitting varieties that we use, I would think, no, I mean, they're really not explicit enough to do such things, I would think.
Yes.